take the derivative on the bottom. That is not quotient rule. It's easier than that. But using L'Hopital's rule, you can get an answer. So those are really nice indeterminate forms. At the beginning of the year, we didn't like them, but now we really do. All right, let's move forward. Let's do a couple more, and then we'll be done. All right, so L'Hopital's rule. Here we go. Got this first one. If I were to try to evaluate it, let's see, plug it in. I'd have e to the 0. That would be 1. 1 minus 1, so I'd get 0 on the top. Now, if you plug in all your x's 0, you would also get 0 on the bottom. So that seems like an issue. You can't really factor and reduce this. You can't use the conjugate of anything. Nothing we really know from the beginning of the year would help us, but we have L'Hopital's rule, and that's going to save the day. All right, so let's now apply L'Hopital's rule. Remember, it needs to be one of those two forms. If it's not, don't use the rule. But here it was 0 over 0, so that's good. Let's apply L'Hopital's rule. The limit stays the same. Let's go for it. The derivative of the bottom is 1. Super easy. Going to do it first. Now let's look. The derivative of the top. I know the derivative of an exponential would be that exact same exponential, but then this 3 would kick down to the front because of chain rule. So here the derivative of the top stays on the top, derivative of the bottom stays on the bottom. You don't really have to write over 1, but now let's apply this limit. So I've got 3e to the 3 times 0. 3 times 0 would be 0. E to the 0 would be 1. And so that answer is going to end up being 3. All right, really nice, really easy. L'Hopital's rule. Very nice way of getting these indeterminate limits done super quick and super easy. All right, next example, let's see. If I were to plug in, here I've got limit as x is going towards negative infinity. Let's see, if I did negative infinity squared, I would get a positive infinity. And then if I were to do e to the negative infinity, the negatives would cancel, and then I'd have e to the infinity, which is infinity, right? So if I were to try to do this limit initially, you would get infinity over infinity, which is indeterminate. Remember, this does not mean no limit exists. This means I don't know what the answer is. So I've got to do something. None of the algebraic things from the beginning of the year will help you, but now we got L'Hopital's rule, and it kind of covers everything, right? It's a really nice rule. All right, so let's go for it. Take the derivative on the top. Still have the limit as x is approaching negative infinity. Take the derivative on the top. Take the derivative on the bottom. I'd have negative, come on pencil, stop messing up. I'd have negative e to the negative x. So I applied L'Hopital's rule once. Let's see if I can get an answer. Let's see if I were to plug in negative infinity now. I'd have negative infinity on the top. And then remember, all of this, e to that negative x, e to the negative x is going to end up being infinity. So this is infinity, so you'd end up getting negative infinity on the bottom. You're like, okay, Mr. Bell, well, it's no longer 0 over 0 or infinity over infinity, because you said those are the only two things that can result in L'Hopital's rule. But really, this is also perfectly okay. The negatives are going to cancel, and then you have the infinity over infinity. So it really doesn't matter if they're plus or minus, as long as they're both the same, either both positives or both negatives. So this one is something where I can use L'Hopital's rule again, right? You're just going to keep taking derivatives until one of the layers is a constant. Remember, as soon as one of the layers is a number, either the bottom or the top, as soon as one of the layers is a number, you're going to get an answer. It's indeterminate when they're both 0 or they're both infinity. So I just have to keep taking derivatives until either the top or the bottom becomes a number. And here I think I'm going to only have to take one more derivative because the derivative of 2x I know is a constant, right? So let's apply a second time and then we'll get our answer. So I still have the limit as x is approaching negative infinity. Take the derivative of the top. The derivative on bottom, you're going to kick out another negative. So that one would go back to being e to the negative x on the bottom. Evaluate the limit now. The top is going to be 2. That's how you know you're going to get an answer, because if the top is a number, there's no way it can still be indeterminate. The bottom ends up being infinity, and if the denominator gets really, really, really big, fraction overall gets small. All right, so L'Hopital's rule covers all of those different algebraic techniques we learned at the beginning, even those weird trig ones like sine of x over x. Hey, guess what? You could use L'Hopital's rule. Or the 1 minus cosine x over x. Hey, guess what? You can also use L'Hopital's rule. Anytime you ever get one of these two issues, you just take a derivative on the top, take a derivative on the bottom, and if you need to do it multiple times, that's okay. You just keep taking a derivative until one of the layers is a constant, and then you will get an answer. Really nice. Really easy rule, L'Hopital's rule, pretty awesome. All right, now let's finish these notes by doing the bottom two, which are a little bit more tricky. They're gonna be just two of the techniques for how you can deal with other indeterminate forms, because those aren't the only two. There's a total of 7 indeterminate forms that really you see in the Calculus 1 and the Calculus 2 course. These are the two nicer ones. The other harder, weirder ones are gonna end up being, let's see, 0 times infinity. That's an indeterminate form. You don't really know what it is. Infinity minus infinity. That's another one. It's not going to be 0. You don't necessarily know that those two are the exact same thing, so they don't necessarily cancel. Could be 0. Could just as easily be anything else. Those are indeterminate. This type of an indeterminate form we're going to tackle with this first example. This type of an indeterminate form we're going to demonstrate with the second one. And then the other 3 we're not going to do, but the other 3, they would be like this next example on the next page. If you're really interested, you could go look it up. You need to use natural logs on this. It's a little bit tricky. Go look at the website answer key if you're really interested, but I'm talking enough on this video. I'm gonna not do it. But let's see, those other indeterminate forms. Remember, that's going to be the first example. This one will be the second example. These other 3 would be similar to what you would do on the next page. So you could have 1 to the infinity power, could have an infinity to the 0 power, or you could have a 0 to the 0 power. So these are 5 other indeterminate forms. This one's going to be pretty easy. This one's going to be pretty easy. Those 3 are a little bit harder. Solving those would be like the example on the next page, but you're not going to see anything like that on the AP exam, so I'm not really going to worry about it. But I do want to tackle this one and this one. All right, so let us go for it, and then we be done. All right, this next one, I've got the e to the negative x, and I've got the square root of x. If I were to try to plug it in, I'd have e to the negative infinity times the square root of infinity. Well, the square root of infinity is infinity. E to the negative infinity is 0. So I do, in fact, have an indeterminate form. But you can't use L'Hopital's rule. Remember, L'Hopital's rule says, hey, take a derivative in the top, take a derivative in the bottom, then you can use L'Hopital's rule. But if you don't have a top or you don't have a bottom, it doesn't really make sense. How do I use L'Hopital's rule, right? So it's got to be one of those 2 forms. This one is something that we can get around, but you're going to have to rewrite it first in order to get around it. So check it out. Let's take this and let's just rewrite it. Still going to have x going towards infinity. Still going to have that square root of x, but instead of e to the negative x, I'm going to just say e to the x in the denominator. That's the exact same thing. Algebraically, we didn't change the value of this expression. Having a negative exponent on the top is the same thing as having a positive exponent on the bottom. So here I'm just rewriting it, but instead of having this on the top, I'm going to rewrite it on the bottom, right? So rewriting that multiplication now as division. And now let's see if I were to evaluate it. You get the square root of infinity, which is infinity. You have e to the infinity, which is infinity, and look at that, right? I took that term that was producing the 0, I moved it to the bottom, and because the 0 and the infinity, they kind of act like reciprocals, when I were to take this and move it to the bottom and have it with the positive exponent, now instead of having a 0 on the top, I have the infinity on the bottom. You don't necessarily always have to do it this way. You could have taken the square root and moved that and had an x to the negative 1/2 on the bottom, and then you would have ended up having a 0 over 0. It's just harder to do it that way. Usually there's one easy term to just rewrite it and put it on the bottom, but the general idea is if I have a multiplication, you're going to rewrite it as division, and that way you'll change the 0 times infinity either into 0 divided by 0, or what we got in this case, the infinity over infinity. So you're just rewriting it as division. That's the strategy for this. So rewrite as division. It doesn't matter which one you flip to the bottom. Either way it will work. It's just usually one of the ways is a little bit harder. All right. So let's see. I got I got infinity over infinity. That's good. So I can use L'Hopital's rule. Let's see, am I still on the screen? Yep, that's good. Limit as x is going towards infinity. Let's see, the square root of x. I have 1 over 2 roots of x. And then on the bottom, the derivative of e to the x. It's e to the x. If you need to, you can write this as over 1 because we're about to sandwich this sucker together. So I have limit as x is going towards infinity. The outside 2 layers multiply, they go to the top. The inside 2 layers, they're going to multiply, they're going to go to the bottom. So I knew it wasn't L'Hopital rule eligible at the beginning, but I rewrote it as a fraction, which was L'Hopital's rule-able. Then I applied L'Hopital's rule by taking a derivative on the top, taking a derivative on the bottom. Now I just simplify it. And now it looks like since all the x's are in the bottom, when you go through and change the x's towards infinity, you're going to get a 1 over infinity. And if your denominator gets really, really, really big, fraction overall gets really, really, really small. All right, so that one, if you have this weirder indeterminate form, if you have the multiplication, the strategy is to rewrite it as division, and then it's going to work. Last one, and then we're done. Okay, let's see. So I got the limit